Welcome to Where is Truth? We're so glad that you could join us. My name is Norm Peckham, and I have with me Dr. Ariel Roth, scientist, author, teacher, consultant to states. We're so glad that you can be here with us. We're going to discuss some of the aspects of our large universe that has to do with, are we meaningful? Are we just a meaningless little thing out in the vast universe? Or is there something that might have more specific relationship and a meaning that makes us meaningful? Where would we start such a discussion?
Well, let's first look at a few pictures of this universe that we have. Here's a picture of the Andromeda galaxy. This is one you can see without the use of a telescope. In the fall and the winter, you look up in the sky, there's these four big stars, we call it the square of Pegasus, and near one of those corners you look and you can see this faint cloud there. That's this Andromeda galaxy. It's one of the units that we find handy for referring to various parts of the universe. These are rather huge things. We're familiar with our sun. Andromeda galaxy has something like 100 billion suns in it.
100 billion, okay.
And it's huge. It would take light 100,000 years to go from one edge of that galaxy to the other.
At the speed of light?
At the speed of light, yes. Now, when we come to our Earth, we find ourselves in a different galaxy. And it's a little hard to see because we're right in the middle of it. But here's a picture of what we think it looks like. And if you look at figure A, you've got, you can see a very fine, narrow, that's because these galaxies are very flat. In the middle, there's a kind of a bump there. And supposedly one of these black holes is there where gravity pulls so strongly that even light can't escape. That's why you call it a black hole. And then, when you look at the lower figure, part B, it's more of a surface view there. And you can see the kind of the black region in the middle, which is supposed to be the black hole, and then towards the side there, you can see where our Earth is. It's on the side of one of those spiral arms that comes out from the center. And we are just one of the suns in there. And again, here we're talking about maybe 100 billion suns in our galaxy and so on. Now, here's a picture of some other galaxies. Not all galaxies are spiral like the ones we showed you. These are lenticular galaxies, and they're the gray, elongated gray splotches you see on that particular picture. The dots that you see there are stars in our galaxy, and these other grayish elongated bodies are other galaxies beyond ours. And we got all kinds of other galaxies out there in our universe. We'll mention that later on and so on. Not all galaxies are spiral. Some are irregular. Some are lenticular, as we mentioned in the last picture.
Are they generally about the same size?
No, they vary greatly. They vary greatly, but they all have a lot of stars in them. This is a smaller, irregular galaxy and so on. This is another object we see in the sky. It's called the Crab Nebula.
Beautiful thing.
It's a very beautiful thing. This is the remains of an explosion of a supernova. It took place in 1054.
Well, they didn't have Hubble telescopes then.
No, you can see, I mean, these are the greatest explosions we know about. Mm-hmm. What happens is that a star, a large star kind of collapses, and when it collapses, it explodes out, and leaves probably a lot of neutrons, you know, a lot of things that we don't know for sure, but this is the remains of that explosion.
Would one of these things attract your eye if you were looking at the sky?
Not especially. I saw one in 1987 in Australia. I just was lucky because these things don't happen very often.
Yeah.
I looked up in the sky there where there was an ordinary star. There was this brighter star there. They only last for a few weeks. Then they degenerate, you might say, into this beautiful thing that we see here, mm-hmm. Per se, and so on. But it's just one of the other things that we have out there when we look in the sky and so on. This is in our galaxy. Then we have comets. You know, these things that fly with a tail on them, type of thing. This is Comet Wild, and it's about 3 miles long. You can see the pock marks on it. It's been hit and so on. They're made of ice and soot and so on, and their tails tend to always be in the direction away from the sun because the solar wind, which are very small particles from the sun, tend to direct it in that particular direction and so on. And here's a picture of one of our planets. So we're getting closer to home here. This is Jupiter, the largest planet in our solar system. And this is astounding. Jupiter is much bigger than our Earth. Now, look carefully at this picture. You see 2 dark bands across the middle.
Yes.
Now, the lower band, and this is a natural color picture, incidentally. You see in Jupiter just the way it's seen. It's mm-hmm. not been enhanced. And that lower band, about the middle of it, the part you can see there, you see this reddish area below.
Little swirl there.
Yeah. That's called the red spot. Mm-hmm. And Jupiter is practically all gases. It's just a mass of gases here. In the center, there's probably a mass of heavier minerals about the size of our Earth, but Jupiter is so much bigger than our Earth.
How fast does it spin?
Jupiter, it 10 hours. It makes a complete circle.
What we do in 24, it does in 10.
Right.
And it's much larger than we are.
Yeah, very definitely.
Does it go the same direction we do?
Yes, Jupiter does. But that raises an interesting question. That is, not all our planets do that. Venus turns in the opposite direction. And this raises a question. How did these things, were they formed by some simple mechanical situation and so on? Because here's Venus going the wrong way.
Now, as I understand it, if in the Big Bang, if it had been spinning, then everything might spin, but it'd all be going the same way.
Yeah, well, this challenges that
whole
simple model. Yes,
I see.
And Uranus also spins the wrong way, not quite as perpendicularly as Venus does. It kind of spins on its side. Uranus kind of points towards the sun with his so-called North Pole type of thing here. But in that red spot that we have there, the Earth could fit into that, and Venus also. They say could go through that red spot. So it tells you about how big this thing. And there are clouds going around in that red spot. Every 6 days, about the clouds make a circle, and people have been observing this thing for centuries. It stays just you know, at that same spot, these gases and so on. A very fascinating universe that we live in and so on. But just a few simple facts about our universe here. Our universe is around, there's about 100 billion stars in the galaxy. We mentioned that to you. There's about 100 billion galaxies in the observable universe.
100 billion seems to be kind of a popular number in this.
Yeah. It's a big number. It's a big number. Our galaxy is rotating slowly, incidentally. For us to make a complete rotation around our galaxy as the galaxy goes, everything goes together, and this, it would take 250 million years.
These are numbers that just boggle the mind. This is big and complicated.
And the thing that really boggles us is that, our sun is going around this galaxy, this huge galaxy, and we're going around the sun, of course.
Yes.
And our sun is traveling at 225 kilometers per second. And we're just traveling along 225 kilometers per second also. But we're just traveling along for our sun, so we're unaware of this. But we're really moving fast.
That's 505,000 miles per hour.
I tell you, that's faster than...
It's huge.
You get a traffic ticket on that one.
Yeah.
The universe is just immense. Just to fly by jetliner from the Earth to the sun, you'd have to fly for 19 years continuously. Very boring trip, of course. Light from the sun takes 8 minutes to reach us. Light travels at around 6 trillion miles in 1 year, and that's called a light year, and so on. And it takes light 100,000 years to travel across a galaxy.
These are, like we said, they're huge and they're big. What are the opinions of how it got this way?
Well, let me just mention this one thing, that the whole universe, as it's thought to be now, and this there's questions about this and so on, because it could be different interpretations related to the Big Bang and so on. The whole universe, it would take light 15, 13 billion years to travel across, or some say several dozen times more than that. And so on. Anyway, ideas about the universe. Well, some say it was created by God. Others say that it always existed. Einstein believed that for a long time during his life. He changed his mind later on. There's a steady state idea. That's the idea that the universe has always been there, kind of, but that matter is being created, man is being destroyed in the universe. And then there's the oscillating universe, and Einstein thought that also a little bit, not very much according to that line, but recently people are thinking about that a little bit. The universe collapses and then bang, you have a big bang and it gets big and so on and so forth. And then there's the traditional Big Bang idea, which has been around for 90 years actually. It's an idea that's survived in spite of the fact that there are all kinds of questions about, how did it start, the precision and so on, the precision of factors. It's unbelievable precision you have to have for the Big Bang to work.
What is necessary for us to be in existence here? Is it just we could be any place in the universe?
Well, one of the things that we take for granted is that, matter is matter and so on. We don't realize that. If you look at matter, it is made of atoms that are highly organized. And these atoms have protons, neutrons, electrons, and so on in them. And some say an atom has 58 different subatomic particles in it. Wow. Here's a picture of some atoms in the, you can see the nucleus in the center there with protons and neutrons and electrons are on the outside. This is hydrogen, helium, and so on. Our simple atoms are right there. Extreme precision is necessary for this. If the mass, we can kind of think of the weight, so physicists like to use the term mass. If the mass of the proton compared to the mass of the neutron, these are in the nucleus, if that varied by 1 part of 1,000, we would not have atoms like we have them. That's how close and precise These parts have to be.
Okay.
In order to have atoms. And these atoms, you know, they do all kinds of things. They make light, they make fleas, and chemists, and or whatever you want, galaxies and stars and so on. And then we've got another example of precision in carbon. Carbon is an extremely important element. You know, our bodies have, for life and so on, you have to have carbon. And physicists, cosmologists have studied these various elements, and there are certain factors that seem to favor carbon that you would not have according to normal steps. And this has been worked out quite carefully. And we talk about the resonance of carbon. Resonance mean that things went just right for carbon to form. It's several different things. It's the forces involved. It's the size of a target type of thing, and so on. And it turns out that carbon is a very favored element. And some people say, well, God must have loved the carbon atom because the resonance is just right for this to happen. So we have this special factor for carbon, and if this carbon resonance had been too small, by just 4%, or if the resonance of oxygen had been too great by 1%, we'd have no carbon around. It looks like that those various factors are all tuned to give us carbon.
I see. Like a well-tuned orchestra.
And then when we look at the orbit of the Earth, another closely related factor, you know, if the Earth were 5% closer or 1% further in its orbit, we'd have no life on Earth. It's just right there in the right place.
So there's a 95% chance that it wouldn't work.
Yeah, but you know, there's so many other factors involved that we could. Then we have the precision of the force of physics. This is really challenging, and this really caused a lot of change in thinking in the scientific world when it was discovered how precise these forces are, the four main forces of physics per se. And we don't have time to go very much into these details, but if we have a strong nuclear force, this keeps particles in the nucleus together.
Mm-hmm.
If that force were 2% stronger, we'd have no hydrogen. But you can't have life without hydrogen, or you'd have no universe hardly. If it were 5% weaker, we would have only hydrogen. And the universe would be extremely boring, you know, and that's all you'd have, is just hydrogen per se, and so on. Weak nuclear force helps in the sun producing our energy, and again, very important factors. This is again a force that works in the nucleus.
You're lining up a whole string of things here that seem like they have to be just right.
Right. And then there's the electromagnetic force. And fortunately, our light comes associated with that. It goes beyond the nucleus of the atom, so we get light type of thing, and so on. But again, it has to be very close, or we would not have the light we want. And what would be the universe without light?
Yeah, right.
And then we've got gravity. And gravity, we're all familiar with. It keeps our feet on the ground, keeps water in the ocean, and so on. Very weak force compared to the strong nuclear force. Only one part out of 10 to the 39th power. It's that much weaker than the strong nuclear force. These forces, they're precisely the right strength. They work exactly in the right place, and the relationship is has to be extremely accurate. The strong nuclear force, the gravity, and the electromagnetic force have to have a very close relationship. If it isn't close, we would not have the sun producing the heat it does from a fusion of hydrogen into helium and so on.
You've lined up probably 6 or 8 things that have to be just about right. Have people calculated the odds for all of that happening that way?
Well, let me tell you first about electromagnetic force and gravity. Those have to be precise in order for the sun to work properly. To 1 part out of 10 to the 40th power. Now, that's 10 to 40th power. Well, we can deal with those figures, but let me give you an example. Supposing we had a pile of matchsticks, okay?
Mm-hmm. Matches.
These are bare matchsticks.
Okay.
This is a pile. It's a great big pile. It's not only 1,000,000 times the size of the Earth, it is 1,000,000 times 1,000,000 times the size of the Earth. This is a big spherical pile of matches. It just barely fit between the Earth and the sun. And it would take you 19 years by jet to fly through that pile. So okay. That's a lot of matches.
It's a big pile.
It's a big pile.
It's a big pile.
Now, only one match in that pile has a head on it. And you're out there, it's very cold out there. And you want that match because you want to start a fire and so on. There's a greater chance that you will pick that match out of that pile without looking than for gravity and the electromagnetic force to have the right strength.
Oh, my.
Now, you asked about combining these things. Roger Penrose at University of Oxford, he tied these things together.
Okay.
He calculated all these things. Now, you calculate probabilities, you've got to multiply them. He came up with the figure. What's the chance the universe could come together, by chance? The figure is 1 chance out of 1, followed by 10 to the 10th to the power of 10 to the 123rd power. Now, let me simplify that just a little bit. It's 1 chance out of 1 to the 123rd power, at power of 10.
That's 10 with 123 zeros after it?
Yeah. When you state it that way, it's got zero. That you have to have that many zeros, and every zero multiplies it by 10, 3 zeros is 1,000, 6 zeros is 1,000,000, 9 zeros is 1,000,000,000, and so on.
Well, now, do the scientists have some idea that if the chances are so small that it's impossible? Have they calculated that kind of a number?
Well, it's generally accepted. It's 10 to the 50th. If it's 1 chance out of 10 to the 50th, you say, well, it's probably impossible.
But this is 1 to the 123.
This is way beyond that.
Oh, my.
Well, what have been responses to this? One response is, well, the anthropoid cosmological principle. This is simply the statement that you ask, well, why is it, how come it's so fine? You just say, well, if it weren't that way, we wouldn't be here. It's not an answer. It's like being out in the desert and you have an oasis and so on. And you ask, where does the water come from? They say, well, if the water weren't there, the trees wouldn't grow. It's not an answer.
Not much of an answer.
Another answer is, well, boy, maybe there were a lot of universes out there. All kinds of them, jillions of universes. Ours just happens to be the one where things are okay.
But you can't measure any of that. That's just a concept, is it not?
Well, it's a friggin' violation of statistical analysis because we only know about one universe. And you could use it for saying anything you want to. I can say, well, the reason cockroaches have legs is because we haven't been in a universe where cockroaches have legs. You can prove anything you want to by that. It's not critical thinking.
Okay.
Then there's the idea that the universe has been created by an intelligent designer. And all this precision that we've seen, I think fits best with that particular idea. The universe rests on a knife edge, and you just alter 1 or 2 of these factors, the whole thing collapses.
And then you ask for that to happen by chance.
Yeah, well, anyway, we can come back to our Andromeda galaxy here again, and it's a marvelous thing. Atoms, it's made of atoms. Atoms have high precision. We've got all these forces of physics, so important, and so on. We have stars going around like our Earth, and exactly in the right place so that we have the right temperature.
Sounds like maybe there was a designer that was making things just right to place something there that was very special.
It looks like a very perceptive creator put these things together. Yeah. When you have such odd chances, it's time to give up the idea, well, maybe God doesn't exist. It's time to look for that God might be the designer, and certainly the scientific data points to that because things are so precise.
So if you were to take a position in which God would be allowed in your paradigm, and you look at the scientific evidence, it gives some pretty good evidence that a God does exist.
Well, I think the scientific data forces you to get out of the materialistic paradigm of science and say, no, look, this couldn't happen. This could not happen.
Okay. Well, we thank you so much for being with us. And here we have looked at a whole lot of different factors, forces that have to be just exactly right to very small precisions, or nothing that we understand or know about could possibly exist. Well, we're not through. We'd like to have you stay with us next time we come by, because we've got some more searching as we look for where is truth. If you would like additional free information about these discussions, there is a PowerPoint resource available on the internet that covers many more details than could be provided in this lecture series. The resource is titled The Bible and Science and is available at scienceandscriptures.com. Be sure to add an S at the end of the word scriptures to get to the right web page. The Bible and Science resource follows the same sequence of topics as the Where is Truth series, but it is divided into 17 separate discussions instead of the 14 videos of the Where is Truth series. The title of the discussions, an introductory outline, and an index will lead you to the topics you want. The Bible and Science discussions served as the resource for the Where is Truth videos.